Hi, this is Mark Kemper with EMS, and in today's video, we're going to look at using a 3D scanner to do dimensional inspection on machine parts like you see here. Okay, to get started, let's talk about why would we want to use a 3D scanner to inspect some of these parts. Because honestly, some of these parts are very simple. Simple holes, planes, things like that. Isn't a 3D scanner overkill for something like this, some of these parts? 3D scanning typically is great for really complicated parts, things that have organic surfaces, things like that. So why would you want to use a 3D scanner to do some of this? Because again, traditionally, hand tools, taking hand measurements will work. Writing a program, putting this on a CMM, dropping it in a fixture, and hitting the inspect button and letting it do it would work. So, is there any benefits to using a 3D scanner? Well, that's what we're going to look at today. Can we do it faster, cheaper, easier, or are there any other benefits of using 3D scanning technology to try to inspect these parts? So we're going to go through and we're going to show you live the time it takes to scan the part and generate the inspection report. We'll put a counter on the screen so you can actually see how long it takes. And then we'll talk about, what are the benefits of maybe using a 3D scanner to inspect CNC machine parts, which typically are more prismatic in shape. Okay, so we are all set up here, and what I'm going to do, like I said, is I'm just going to go through, scan the part, and then run the inspection routine, and then I'll explain what I've done. But the point here will be to see how fast we can actually do this and actually get from scan data to an inspection report. I'll put a timer up on the screen, but I'm also going to do it here on my phone so I can kind of see what the actual time is. So we'll go ahead and get started, and what I'm going to do is take the scanner and scan the part. And again, I will explain when we're done how I've set this up, okay? But I'm just going to go around the part and scan it, okay? And it's all line of sight. And if you want to know more about this, this is the HandyScan Black Elite, which has an ISO certified accuracy of 9/10 of 1/1000 of an inch. So it's very good for this kind of work. And if you want to know more about that, we've got a demo video that goes into great detail. We've got videos doing accuracy tests. All kinds of information you can learn about this scanner. Okay, so we call it digital spray painting. The more perpendicular I am to the surface, the better data I'm going to get. I'm just working around trying to get in these holes, try to get down on the bottom of the part here like you see here. Okay, you can't overscan the part. Certainly you can just keep going over and over and over it till you get what you need, so it doesn't hurt to keep going over the same areas. Okay, so once I think I've got it, then I can always stop and look at the data and start and continue on. But I'd say that looks pretty good. I'm going to hit stop scan. And then what I'm going to do, and again, I'll explain everything I've set up. I'm going to finalize the scan. That's just the final process to process the scan data. And this only takes usually a second. Just the longer you scan, the longer it takes. It's just going through, and there's some settings you can set, and it's processing those. For inspection, I've turned most of those off. Now I'm going to export the mesh, and we're going to call that round part scan 1. That already exported it. I'm going to go over to my inspection software. I've already created all my inspection, and again, we'll talk more about that. But I'm going to come in here, and I'm going to import that part. And then I am going to process the inspection report, okay? So I've imported the scan data. You can see it's obviously not in the correct coordinate system. I have just ran my inspection report. And now, if I want to actually export it, I've run the inspection, I should say. Now I'm going to actually generate the report itself. Okay, and let me slide this over so you can see it. So here's our CAD data. Here's our scan data. Here is our first alignment, which is an initial alignment. Then we did a datum alignment, etc. But basically it's done, and we're at just under 3 minutes, okay? But let me just keep going here. Here's our color map, and then we've got all of our tolerances that we've done, all of our inspection. This is a linear dimension. We've got positional tolerances. We've got cylindricity. We've got, I already mentioned positional. Whatever you want to inspect, you're going to build into this. But basically, I was able to scan this part, import it into the inspection software, run the report, and spit out a PDF report in roughly 3 minutes. Okay? So now, if we were just doing one part, am I going to go through and do all of this setup to just do one part? Probably not. I mean, it'd just be easy enough to measure it by hand, or even go on a CMM and take some manual measurements. But let's say I'm doing 20, 30, 40, 50, 100 of these parts, and I can inspect each one of these in 3 minutes and do it very accurately and very fast. Does that make sense? The other thing is since we're doing it digitally, all of this can be in a database. So not only can I spit out a PDF file, I can put all of this data into an Excel spreadsheet, and I can look at SPC software and different software that does analysis or trends. Maybe over time these parts are going out of tolerance and we don't know why. So, but I can quickly look at this part and realize I've got some problems. Yellow's bad, red's bad, so there's definitely some issues with this part. And in fact, almost every tolerance or everything I've inspected here is out. So that's the whole setup on a simple part like this. What we'll do next is I'll kind of explain the setup so you understand how I was able to do this in under 3 minutes. Okay, so let's talk a little bit more about this setup and the giving me the ability to do this fast. So first of all, you see this setup here. Why am I setting the part up like you see it here? Well, a couple reasons. One is, if I want to do this fast, I don't want to have to be putting targets on the part. And typically with smaller parts, we don't, we come up with something else. It's just easier. Because the scanner just has to see targets around the part. They don't have to be on the part. And as long as we fixture it in a way where the part isn't moving, we're fine. And since this is all non-contact, you would look at this, if you were inspecting this on a CMM the way we have it set up, and it's just not very rigid, the part would move around. But we're not touching the part, and as long as I kind of rotate this thing slowly, it's secure enough on here that it's not going to move around. So we use these type of fixtures all the time, and we can configure it any way we want to inspect parts. Because what this allows me to do is scan the part from all directions and get the data, okay? But you may have noticed, well, why didn't you pick up these, these metal bars here or any of this other data? And that's because I set up what's called a template. So I'll show you here in the software. So what we have, you can see, this is all pre-stored. And what I did was I pre-scanned the targets. So you just go into the scanner and you say, scan all the targets, and then you save all this info in a template file. And then the other thing I did is I created clipping planes. So you can see I've got like a box that's kind of inside. There's those bars. You see the targets on the bars. And that I just quickly drew a line and it makes a plane. So setting this up took me 20 seconds to scan the targets. Let's call it a minute to scan the targets and put on some, add these clipping planes. And then what happens is, now when I scan, if it's outside this little box I've made, it just ignores it, okay? It gets clipped off. The only thing that ends up in the scan data is a little bit of these rods that are holding up the part, but in our inspection, once data is a certain distance away from the part, it just ignores it. So it doesn't even factor into the inspection report at all. So I'll leave these turned on because you can turn them off, which I had the first time. So now when I go to scan, it already knows where all the targets are, and it knows where that clipping plane is. So you can see as we move around, if I come over here and scan down here, you see it's not getting anything, okay? So this allows me to set up an inspection routine where I'm not having to scan the part, target the part, and then maybe scan the part, and then flip the part over and do a second scan and merge those scans, and then go clean up all the data. If we're trying to do this fast and easy, we don't want to do all that. So a little bit of prep work will make this, give us the ability to scan this and run in a report in roughly 3 minutes. So a little bit of prep. And again, you're not going to do this if you're scanning one of these. It just wouldn't be worth it. But if you're doing 10, 15, 20, 30, 40, this may be a viable setup for you. It's fast, it's good accuracy, it's super easy to use. Anybody out on the shop floor could do this. Somebody else can write the inspection report, and we'll show you how that inspection report was written. That can be done offline, and the operator running the scanner, really all they need to know how to do is push the button, scan until you fill up, you get the part all scanned, hit save, import it in that inspection, and hit inspect. So you can make this very simple. So this can be very fast. It's really good accuracy for a handheld device under 1/1000th of an inch. And actually, on small parts like this, we see much better accuracy. But that's the stated ISO accuracy for this. But parts like this, we're seeing 2 to 5/10ths of 1/1000th of an inch all the time. So we can get really good accuracy, and we can do this out on the shop floor. We don't need a dedicated room in an environmental controlled environment for like a CMM. This is going to be more repeatable than taking hand measurements because, as long as you get good scan data, you're going to get repeatable results. Where people taking hand measurements are only as good as who's taking those measurements. Somebody's in a hurry, or they don't put those calipers or those different micrometers and things in the right position, you could get a false reading. And if you're doing it by hand, then you're writing it down or plugging it into a spreadsheet manually. Once we inspect it, we've got all that digitally. So we'll set up one more part, just a part with a little more complexity, and we'll run that one just to show. But hopefully you get the idea here of what you can do with a 3D scanner, even on simple machine parts. All right, so I've got this part here, this bracket, and this part's a little more complicated. But the beauty is the same fixture, the same setup, everything I've done will work just great for this part, or really any part of this size. I just moved my little post holding it up a little bit. So we'll do the same thing again. We'll run a timer, and we'll go ahead and get started here. So the same thing, I'll leave the clipping planes on this time so you can see them, okay? You can just hide them, it just makes it easier sometimes to see. So I'm just going around and scanning it. Now the other thing too is I only really need to scan it where I'm measuring, right? So holes, planes, things like that. So if there's areas of the part that I really don't care about, I really don't need to scan them. No different than a CMM or a, taking hand measurements. If I don't need stuff, don't bother scanning it, okay? It's just gonna, when we run our report, it's just gonna, ignore that area. So I'm trying to get the bottom here really good because that's an important feature, okay? And again, just getting into the holes and any of the areas. But like these internal side walls, those are just clearance. I definitely need the hole in there, but some of this stuff is not really critical. It's really typically the holes and some of the key planes, any mounting surfaces. So again, once I think I have what I need, I will finalize the part. And then we will go ahead and export it. Call this bracket scan 1. We go over to our inspection software. We import that data. We go ahead and process it. So this is the actual process of aligning it, merging it, or aligning it, and then running all the inspections. So you can see here graphically what that looks like. We hit generate report. We are going to take that template. So you can build all kinds of report templates in the software, and it's going to go ahead and spit out that report. Okay. So again, there's our CAD file, there's our scan data, there's our initial alignment, datum alignment, a 3D color map, and then all of our different measurements, okay? So whether it's flatness, positional, concentricity, whatever we want to measure will be in this report, okay? So what we'll do next is we'll actually go in and show you how to create these reports offline, so that then all we need to do is import the scan data, run it, and then export the report. So we'll show you that part of it as well. But again, you can see in a matter of minutes, even a part like this, I can scan it, import it in, generate my inspection report. So again, next, let's take a look at what it takes to create those inspection reports.
All right, so let's take a look at what it takes to generate an inspection report. So the first thing we need to do is import the CAD model. Okay, so the 3D, what we call nominal data. This is the original CAD model that was designed, and then typically somebody would design it in CAD, and then in this case we're doing machining. They would generate their CNC cutter path and send that out to a mill. Now the nice thing with this is we can do this offline. So the minute that CAD file is done, we can start building our inspection report. We don't have to have the scan data. All we need is the CAD, and assuming there's a drawing that calls out dimensions or tolerances or whatever it may be, you would probably reference that as well. Okay, so let's get started and we'll walk you through the whole process. So here's our CAD file. First thing we're going to do is an initial alignment. So that means when we do import the scan data, we do an initial kind of global alignment, okay? And that just gets the part because the scan data is not in the same coordinate system as the CAD system, and it's just going to bring it and line it up on the CAD file. And then from there, you're typically going to do a second alignment. That would be a best fit, an RPS, a datum, a 3-2-1, etc. If we're trying to imitate a typical setup on a CMM, they typically use a datum alignment. Now, I'm not going to go into too much detail on this, but it would be a typical or similar alignment to what you might see on a CMM when you're fixturing up a part. So my first datum, which will be my most critical, will be this bottom plane. And then since this part is round, I'm going to use one of these cylinders as my second datum setup. So there we go. So now I've created my datum alignment. We can turn off the tags here so we don't have to see them. And then typically what we're going to do, we'll do a 3D color map. Now this just does kind of like a heat map or a comparison. It's just a nice, gives you some nice information, but you don't get a lot of actual data out of it. But you can definitely see trends and quickly see what might be going on the part. We're going to set this global tolerance of 50 microns. I'm working in millimeters. You can, of course, work in inches. So we've got that 3D compare done. And now we're going to go in and start doing our dimensional tolerances and our gd&t. So we go to our dimensions tab, and we just start telling it, the things we want to measure in the order we want to measure them in. So a very typical one is a positional tolerance. So we'll go ahead and click here. We'll click on this cylinder here. Now, if it was a bolt pattern, you could do it, but or click pattern, but these are actually not in a bolt pattern. They're actually staggered. So we'll just do them separately. So we're just calling it out, and we'll stick with that 50 micron tolerance on these positions. And then I'm just going to add a second group. Each group is its own page on the inspection report. So there's our first one. And then maybe we want to do concentricity between this inside and outside. So in order to do that, we're going to flag a datum. We'll put the datum on the outside. We'll call this datum C. And then we'll pick concentricity. We will pick the inside. We'll, let's say, we'll stick with the, for now, the 50 microns on this as well. And we'll hit OK. So there's that. Let's add another group. And let's say flatness on this top is critical. So let's go ahead and check for that, and maybe that will set at 0.035, 35 microns basically. And let's add another group, and let's do some, let's say cylindricity on this main cylinder is critical. We'll flag that, and we'll make that, let's make that 40 microns. Okay, so you're basically just going to and adding all your measurements, and let's just do one more, and we'll just pull a couple radial dimensions off of our outside and inside diameters. Let's say the outside is not that critical. We'll make it 100. And the inside, let's say, is critical, and we'll make that, let's do 35. Oops. Okay. So that's it. Once we're done creating this, we would just save this file. And then once we get our part scanned, it's the same process as we showed. We just import the scan data. Okay. So it's going to come in. There's the scan data, which again is not in the same coordinate system. We just hit the little rebuild button, and now it's going to run that report. It's going to do the initial alignment, the datum alignment, the color map, and then all of our gd&t and measurements. Okay, so there is everything. If you look at the color map, oops, I turned it off, and turn off the gd&t. So, this is nice. It just shows you trends. Obviously, we can see some issues. If 50 microns, everything within green is within 50 microns, going to the red would be plus and going below is minus. So I can tell right away we've got issues on this part. It's sloping down. I can see issues with the holes. Now the bottom looks good because that's our main datum, and it lines up obviously to that. So it's nice color map, at least to see things. Now, if we look at our tolerances, or sorry, all our callouts, we can see now you can see different colors based on the results, and we'll get into this a little bit more in the report. But we can tell anything in red is out of spec. You don't see the actual values yet. You'll see those in the report. Anything in green is within tolerance, and anything yellow is approaching out of tolerance. So we can look at it here on the screen. We can pick any dimension and look at the actual results and see the actual values. So for example, the first positional tolerance, the actual value was 0.1084. The tolerance was 0.05, so obviously that one failed. So you can see all this by clicking on different things, but ultimately we want to put this in a report so we can email it or send it to somebody. So we're going to go to the Generate Report tab, and then we'll pick, there's different formats, different templates essentially, and then we can generate the report. So once the report is generated, and you can have it populate all this stuff, you can see we've got our logo on here. So let's look through this report. Now this report can be output as a PDF, PowerPoint, Excel. Typically we send out a PDF and then we can email it to people or print it out. So here's our CAD file. Here's the scan data. Here is the initial alignment, the distribution. You can see the min, the max tolerance, the average, the RMS, the standard deviation, etc. There's our datum alignment. So we see that. And then here's our 3D compare. Now you can see the results of that after that datum alignment. And usually you'll see a nice bell curve. So obviously this part is going in and out of tolerance. So it's, it doesn't look that good. And now we look at our different groups. So there's our positional tolerances. Here's the actual values, the tolerance and the actual value. Here, group 2 is our concentricity. So we can see that's out by quite a bit. Here is our flatness. That's out as well. And here is our, what have we got here? Cylindricity here on that main cylinder. That's bad too. And then finally, we've got the radial dimensions, which one of them is in and one of them is out. So we can tell right away this part is not good. So if we're doing some first article stuff, we would look at this and say, man, that's pretty bad. Now, let's say we've scanned 10 parts. All we got to do now, and we can automate this, but we would just say, okay, let's pick our second set of scan data and go ahead and run the inspection process. So once this report is built, you just have to import the next set of data. It's automatically going to run it. And then I just click the Generate Report button, and I have my second report. So once this inspection file is created, as you see, it only takes a minute then to run the report. And you can automate this so that every time it sees a new scan file in that directory, it imports it, runs the report, and spits out a PDF file. So we can fully automate this inspection process once we've run this report. So, if you're doing one part, maybe it's not worth all the effort. If you're going to scan and inspect, let's say 10 or 15 or 20 of these, then it may make sense to write this report and just run it.
So that wraps up this video on using a 3D scanner to inspect machined parts. Now, is this a viable alternative for you? Well, it just depends. But what we've hopefully learned today is it can be very fast to do. It can be pretty easy to do. We can get some very good accuracy with a scanner like the HandyScan Black Elite, less than a thousandth of an inch, which for a lot of people is more than enough for their type of parts. So we've got good accuracy, ease of use. We can do this out on the shop floor. We can put together some very simple fixturing to make it fast and easy and get some pretty good throughput. So if you'd like to maybe see if this is a viable alternative for your type of work, then reach out to us. We'll put some information in the description below, and you could send us a part, and we can do this virtually. We do it all the time with a customer's part, and we'll do a live demo and scan it, or we can come out to see it, either way. But let's see if this would work for your type of parts. So again, you're going to get good accuracy, you're going to get digital data that you can put into a database, and anybody can run this scanner. You can do the programming offline, and if you're doing, any kind of quantity of parts, this may be a good alternative to a traditional CMM or taking hand measurements.